Chapter 13, Properties of Liquids. So earlier in Chapter 3, in Chapter 1, we talked about solids. And there were amorphous solids and there were crystalline solids. The amorphous solids, it was like a frozen liquid. Molecules were orientated randomly as if it had been a liquid that had just flash frozen. The crystalline solids, all the molecules were in regular repeating three-dimensional lattices. In Chapter 12, we did gases. And gases are at the other extreme. All the molecules have escaped from each other. We take up their entire container, and they take up the maximum amount of space possible. This chapter's on liquid, it's in between. Like a gas, a liquid is a fluid, and it can flow. Like a solid, a liquid is a condensed state of matter. And so it has some properties of solids and some properties of gases, and it's right in between the two. So liquids are intermediate between gases and solids. The particles are close to one another like in a solid, but they're able to flow by each other like in a gas. So they're a condensed state of matter and they're simultaneously a fluid capable of molecular movement. There are significant attractive forces in the liquid, and that's why you have a condensed state of matter. All the molecules are binding onto each other pretty tightly, and that keeps them in the condensed state. And so whereas a gas had almost no intermolecular forces whatsoever, a liquid still has most of its intermolecular forces holding them together. Evaporation. This is when a liquid evaporates into a gas. The word vapor means you're finding something in the gas phase, but whatever this thing is normally a liquid. So we say water vapor, not water gas, because water is typically found at room temperature as a liquid. So things that are normally found as a gas are called gases. Oxygen gas, nitrogen gas, they're gases. Vapors are the gas form of a chemical which is normally found as a liquid. And so both gases and vapors are gases. It's just that a vapor is typically associated with something that's liquid at normal conditions. So evaporation is when a liquid evaporates into a vapor. Condensation is when the vapor condenses back into a liquid. So you have evaporation and condensation. Sublimation, when a solid goes directly to a gas and skips the liquid state altogether, it sublimes. If the gas goes right back to the solid, it deposited. That's deposition. So we have sublimation and deposition. And dry ice sublimes. That's why it's called dry ice, because the solid carbon dioxide evaporates directly to gaseous carbon dioxide at 1 atmosphere of pressure. If you have more than 5 atmospheres of pressure, you can get liquid carbon dioxide. And in fact, liquid carbon dioxide is used a lot in the food processing industry. It's how we get decaffeinated coffee. Soak the coffee beans in liquid carbon dioxide, and that's a nonpolar solvent which extracts out the nonpolar caffeine. And now you have coffee beans which have most of the caffeine removed from them. And then you can evaporate the carbon dioxide, and you're left with all this caffeine powder, which you can then sell to companies that add it to things like Red Bulls and Monsters and every other energy drink that has an insane amount of caffeine. So it gets used somewhere. Any questions on sublimation or deposition? Iodine sublimes, and also interestingly enough, ice sublimes at negative 20 Celsius. This is why things can freeze or burn in your freezer, because your freezer is negative 20. And so at negative 20, that solid ice in your freezer will skip the liquid phase and go directly into the gas phase. And so you can freeze dry things this way. You can freeze or burn things this way. The fancy scientific word for this is lyophilization. When you freeze something and apply a vacuum so the ice evaporates off. And it skips the liquid phase because it's subliming. All right. So again, a liquid evaporates to a vapor. and the vapor can condense back into a liquid. If the bottle's open, evaporation continues until all the liquid's gone. Then it's an empty bottle. If the bottle's closed, you'll get to an equilibrium because the molecules are trapped in the gas phase here. There's nowhere for them to escape to. And so they build up. And at some point, there's enough molecules in the gas phase that the rate of evaporation becomes equal to the rate of condensation. And now we've come to an equilibrium. Because for every molecule of liquid that evaporates to the gas state, a molecule of gas condenses back to the liquid state. And now we have what we call a dynamic equilibrium. It's dynamic because the molecules are perpetually moving. Liquid is perpetually evaporating. Gas is perpetually condensing. It's an equilibrium, though, because the numbers become stable. You have so many gas particles, and every time one pops into the gas, one goes back to the liquid, and so the amount of gas particles stays constant. And so we call that a dynamic equilibrium. The states remain steady, and if you're just looking at it, it looks like nothing's happening, but on a molecular level, it's actually really active. You have a lot of evaporation and condensation happening. It's just that the rates are equal to each other. The vapor pressure. This is the pressure exerted by a vapor that is in equilibrium with its liquid phase. And this is independent of how much liquid you have or what the surface area is. It only depends on temperature. The higher the temperature, the higher the vapor pressure. Volatile liquids. These are liquids that have very weak attractive forces between the molecules, and so they evaporate really easily. The stronger the intermolecular forces of the liquid molecules, the tighter they bind each other, the harder it is for them to evaporate and escape from each other. If there's really weak forces holding them together, they evaporate super easily, and we have a volatile liquid. Therefore, volatile liquids have really high vapor pressures as a result. So here we see measuring the vapor pressure of a liquid. We add some water vapor into this vacuum, and we see it pushes down 18 millimeters, meaning that the vapor pressure of water in that sample is 18 millimeters mercury of pressure. Surface tension. Here we have the resistance of a liquid to increase its surface area. Molecules. Basically, what we look at are the two types of forces. How much does a liquid like itself, and how much does a liquid like what it's touching? So, mercury forms spheres here because it's not making any constructive bonds to the container it's touching, but it likes to bond to itself. So it tries to minimize bonds with something else and maximize bonds with itself. Same thing will happen if you put water on wax paper. It'll beat up because the water cannot make effective bonds with the wax, and so it tries to maximize its internal bonding and minimize bonding between the water and the wax. And so water will beat up on wax. If you put water on glass, it'll spread out because water does make effective bonds to glass. And in fact, water likes touching glass more than it likes touching other water, which means it wants to spread out as much as possible. And so those are our two possibilities here. The surface tension will increase with increasing attractive interactions between the molecules. The more the molecules hang on to each other, the less likely they are to let each other go and make it spread out. They want to keep themselves in a ball. And so we have a demonstration here with some Japanese yen coins.
Hey, have you guys ever heard of the spider that sits on top of the water and uses the water tension to actually swim, actually float above the water? It's like this weird African spider, but it's pretty cool. Pretty big too. It literally spreads itself out evenly so that it displaces its pressure evenly, so that when it's on the water, it uses its little the little things on its legs that actually propel it through the water, but they keep it above the water because of the surface tension. It's actually pretty cool. Yep.
I've seen a lizard that runs on the water because it's so quick and.
Yep. But this thing floats, like it floats above it. It's kind of strange. I don't know what it's called. Hold on. Let's see here.
All right. Here we have Japanese yen coins. We use these because they're made out of aluminum. Aluminum is about 2.5 times denser than water. So we take an aluminum coin, it sinks. Like you'd expect for something that's denser than water. However, water has an extremely high surface tension. So if we're gentle, we lower our coin in. The surface tension of water holds it up. So check it out, and actually you'll notice it's indented. But the water molecules are holding on to each other so tightly they refuse to let that coin sink. Because that would mean the water molecules would have to let go of each other. So go take a closer look at it.
Hey, Mark.
Yeah?